everybody to this last session of the day. Yeah, maybe a bit less. Okay, so my name is Benjamin. I'm trying, or right now we are trying to talk to you about what we did at work, which is trying to bring life to one new device to Android. So I don't know how many people from your side are familiar already with trying to port Android to new devices. Someone else already probably in this room? Only a couple of guys. How many people have attended to the presentation from Marco this morning? Okay. So just a few side notes about me. So I'm working as a software architect for Alcatel-Lucent since quite a while, so it's been nearly 10 years, and I'm mostly involved in what we can call all the Linux low-level and platform drivers. So I'm really used to integrate different BSPs from different vendors, mostly for Linux. I'm also responsible for many contributions to open source software. So I'm either the leader or the contributor for many projects, for example, the OpenBricks and the GeeXboX projects, which are embedded build systems for Linux, which are pretty similar to Buildroot or also to OpenEmbedded. So this is the kind of area that I'm actually working on. And I'm also a regular speaker to different editions of the Embedded Linux conference. So I made 3 different conferences over the years. My personal experience, as I said, is mostly related to Linux embedded systems. This is really the kind of area where I come from. So I really know a lot about cross-build systems, hence the creation of the OpenBricks project that we did. And I used to work with many, many different vendors and different architectures. So I'm used to different embedded x86 architectures, but also used to work on PowerPC over the time, and MEPS64, and also some ARM, ARM9, ARM11, either for Broadcom, from Marvell, from Freescale, or for TI. So my experience really is trying to port new devices and bring life to new boards to Linux and give them birth. And since, I would say, quite a few months now, within my company, we are trying to bring these new devices to Android. So this is quite a challenge for me because for having been worked on Linux for over 10 years, switching now to Android is actually quite different. So what you may have heard is that Android is kind of sort of a derived version of Linux. We will see that it has not that much in common except from the kernel. So I'm pretty much a newbie about Android, but I'm also learning about it a bit more every day. So what I would recommend to every reader is these 2 excellent books. So one of the books has been written or is currently being written by Karim Yagmur. We did the keynotes this morning. So this is called Embedded Android. So for anyone who tries to implement new devices and port new devices to port Android to new devices, I would really recommend this book. Also, one really great book for those people that want to understand the architecture of Android, but also want to learn more about how to write new applications for Android. I really recommend reading the Learning Android from Marco Garganta, and these really are 2 really good books. So a bit more now about the work context and the why we came on this subject. So I'm working within Alcatel-Lucent. I'm working within some division that makes enterprise desktop IP phones. So these really are phones that are meant for enterprise, so require some kind of level of security, and really are only meant for IP communications. The challenge that we have right now is to try to port Android to this kind of new devices, and we'll see that actually this porting Android on different devices is something not that easy. But porting Android to some devices where it's not really has been meant to be ported is a way more difficult challenge. So for example, in this case, our device is not like a regular smartphone or regular tablet that you may find. For example, it's always connected. It has no battery. Also, it has no GSM or CDMA, so no phone or no modem. So it's really different. It's always docked. It has no screen that you can rotate, no accelerometer, no GPS. So this may sound like really small things, but in the end, it really makes a huge difference compared to the other kind of Android devices. Also, for example, we are using Ethernet connection for our IP phones, which is something that we will see in a few slides, is something that is really not meant to be used by a regular Android distribution that you may find. So within this subject, we wanted to switch directly to ice cream sandwich. So for those of you that are not necessarily familiar with the ice cream sandwich, Google always made some what they call the device compatibility document, which is also called the CDD. This is some documentation from Google that explains what are the requirements, both in terms of software but also in terms of hardware, that your device needs to implement in order to be really compatible, a really Android-compatible device. So this is not, you do not necessarily need to do that. The only really requirement for you is that if you want to ensure that your device will be certified by Google and then will be allowed to access to the marketplace and will be compatible with the different applications that you can find, then you need to be compatible with what Google wants. So for example, for ice cream sandwich, the document is like 25 pages long, but the main consideration that we have is, for example, in terms of hardware, the memory is, the minimum is around 512 megabytes. Normally it's 340, but well, depending on physically you just use 500 megabytes. For the storage, you also have a minimum of 2 gigabytes. And for the display, you have some really minimal resolution in order for the applications to be well displayed. Also, you need some hardware for the graphics, and you do not have any possibility to modify the Google APIs in the framework. You can extend it, but you have no capability to modify it. So everything should remain compatible. And one of the really tricky points that we have seen in our project is that the Android telephony features that it is meant by Google is actually only referring to the 3G or CDMA. So we are actually trying to build some IP phones, and the IP phones is using just voice over IP and not regular telephony through a modem. So this is not a phone in Google terms. So the regular IP phone is not a Google phone. So this is really a key point that we have to address. So if you want to go with Android, you have to start somewhere. So of course you can go with directly with Google. So you check out the AOSP from the Google website. The URL is just put over there, and you have the up-to-date support for Android, but also it's really limited in terms of devices, mostly except from the Galaxy Nexus that has been released and the only official device from Google. There's nothing much, maybe a bit of support of the Penderboard, but not complete. Also, you can use the Linearo AOSP, which is taken from, which is a ripped version from Google, which is much more integrated. So the Linearo guys made a really huge job on that. And we will see the Pro after that, but it also has a much wider support than what Google just provides. Also, you can use the AOSP version from CyanogenMod if you want, which is also some ripped-off version from Google, but which is mostly be done to support devices that are already existing as commercial products. So if you want to work and design your new product, I would recommend using Linearo better than Cyanogen. And of course, you can also just take the AOSP BSP that your SoC vendor has provided to you. It may be outdated, so you do not necessarily have all the support that Linearo or Google will provide, but it's probably the best support that you may have for your SoC. So on the example that we'll follow, we are going to consider that we are just using some TI OMAP4 based board that can be derived from the Penderboard, and using the Linearo sources because this is one of the most, I would say, supported or the better supported distribution that you may find for this hardware. So you probably have seen a lot of conferences already from Linearo and the added value that they have done on the AOSP. Most of them is that they have added a lot of new extra packages on AOSP. So for example, they have added FFmpeg PowerTop for power consumption monitoring, the ARM DS5 profiler. but also they have included directly U-Boot and the kernel sources directly within the AOSP, and which is something really, really important, they have integrated BusyBox within the AOSP, which is really helpful for debugging and development. They have also optimized a lot of packages that comes from Google, so for example the Dalvik VM, but also all the PNG, JPEG, or OpenSSL libraries. They have been optimized for ARM instructions, but also for multi-cores, so they are running much faster than the versions that are provided by Google. And they also include whatever they can in terms of proprietary firmwares, so for example, for different Bluetooth chips or Wi-Fi chips. By comparison to the ICS sources that you may find from Google, they have much wider support. So for example, the Panda board and the Beagle board from TI are supported, but also some chips from Freescale, IMX5 and IMX6. Not yet IMX6, but soon, and the Snowboard from ST Ericsson and the Origin from Samsung. So if you want to go and take this AOSP, you now want to just create your new device. So I just try to put you a couple of, I would say, guidelines of how to add your new device. So the important thing, but Marco already presented a couple of these things on this morning, is to create a new entries within the device directory on your AOSP sources. So for that, you usually just create a directory device/my company, and then you can put a my device directory, which will contain all the necessary make files. So one of the really important files to use, of course, is the vendor setup.sh file, which has to define your new device. And for this version, it's the engineering version. You may also add the debug options. But this is the file that creates a new entry when you hit launch and trying to build the AOSP. Also, you have, of course, a set of other files, like the mandatory Android.mk file that is just used to include all the following make files, and the different other kind of files, so Android products.mk, but also your device.mk, where you have to specify all the different make files that you want to include. So, of course, the best thing for that is to try to include or to get copy from some generic device or some device that is close to the one that you want to build. But this is the kind of place where you can, for example, modify the product brand, the product device, and the product name, which just describe your device. And the values that you put here will be really important because they will be used later on by some scripts within the runtime system. Next thing that you might want to do also is to create some device.mk file. So again, within this file, you have a lot of specific rules, makefile rules that you may have to put. So for example, you get the product copy files, which is some macro that defines all the files that you have that you want to see back within the runtime system. And you also have the product package macro, which defines what are the packages that you want to build from the AOSP and include within your distribution. Same goes for the property overrides. We'll see that a bit later on, and different other kinds of makefiles that you want to include. One good file that you may have to check is the build/core/product.mk makefile. This is one top-level makefile that is included by all of these makefiles within the build system. Within this file, you may want to check out, but you may have a look and see most of the, I would say, makefile variables that you may find. So this is really useful because you do not have that much documentation and information within AOSP otherwise. So just have a look at this file. But otherwise, what you need to do is create the board.config.mk file, which is some place where you define all the product-specific compile time options that you want. So for example, you may set the target board platform, specifying which kind of platform you are trying to build. So in our case, it is the OMA 4 from TI. You also have some other options which are really specific to the target or the compiler that you want. So here you just say that our device is ARM v7. So you want to optimize the compiler to produce binaries for ARM v7 and not lower, so that you get the maximum performances. Same goes for the Neon. So if you have some chip that is capable of supporting Neon instruction, it's a good thing to add it here. If you have a Tegra 2 from NVIDIA, for example, you do not have Neon, so just do not put that here. And also some other variables are really important, for example, for the file system and partitioning. So this is the place where you just define, depending on the topology of your SD card or your eMMC, what are the sizes that you want for your system partition, for your data partition, for the cache, and so on. You can also define what kind of file system you want to use. So for example, here you just say that you want to use ext4 as the file system. You may just use other options. But this really helps the build system of Android to define what are the options that you want and how you want to build your device. Same goes for other flags exist in order to set up the recovery, or also to specify whether you want to override the init.rc file from Android or not. Another thing that is really important when you are trying to make your own device is that within the makefiles there is some really useful macro that you can use, which is the device package overlay. So within this, actually, as Marco said this morning on the presentation, one good thing is trying not to mess around the already existing files from the AOSP, because otherwise you will get a lot of issues trying to merge new patches from Google when you are trying to update. So having this overlay, you actually can just create a new tree and new directories of the files and create your own versions of the files that you have to modify. So this really avoids you from patching the files from Google. You just change whatever you think is interesting in these files, and you just put it right here. So this really is a good approach. So within the overlay directory, usually what you may change are these three files from the framework's base. So for example, the config.xml, the dimension from XML, and the storage list from XML. We just defined what are the mount points that you want, if you have one SD card, if you want it to be auto-mounted. And the config.xml got a lot of settings that you may want to customize about your Android. So whether you have telephony support, what are your network connectivity capabilities, many things can be customized within this XML files. So if you want to really customize your device, just create new files and put these new values within these files. Then, of course, you will require some bootloader. So Google provides one implementation of, I would say, generic bootloader, which is pretty much useless, which is located in bootable/bootloader/legacy. Most of the SoC vendors will just replace it by U-Boot with support for the Fastboot protocol. And regarding the bootloader, you have two possibilities. Either you just provide within the AOSP the pre-built version of the bootloader, or you just integrate the U-Boot sources within the AOSP and try to build everything directly within AOSP. So when specifying the different commands in the board config.mk file, you may just define, for example, if you want or not, for example, with the target use U-Boot or the target no bootloader, specifying false or true, you just define whether you want to use the pre-built version or not. And if you are not using the pre-built version, then, for example, you just specify the U-Boot config, and you specify which is the default config. And so when the system is trying to build U-Boot, then it will use, for example, in this case, the omar4-panda-config file, and the U-Boot bootloader that will be built will be using the configuration file that you have here. So if you have a specific U-Boot and you have defined your own specific customization for your own specific device, just replace this generic name by your device, and everything will be built for you. The kernel is also one major thing that has been changed in Android. So I won't go any further on that, but most of the many patches have been added on the Android kernel. So there has been a lot of talks about that, but most of the changes are around the binder, which is the new IPC systems, the PMEM that we have talked about this morning, the wake locks, many other changes. If you're really interested in the details, you may have a look at the elinuxwiki.org wiki. It just sums up all the changes that happened on the kernel, so it's really well documented. I won't go any further on that. And what is really important to know is that the kernel, I would say the kernel policy within Android is usually to avoid having modules. So there is multiple reasons for that. First is that all Android devices and the build that you do for devices is usually meant to run only on your devices and not other devices. It's not like an x86 distribution that has to run on the most hardware as possible. So everything is really built as a static configuration, and you just avoid having modules. Also, it's faster to load up because you do not have modules, and the footprint is also smaller. And also one of the things is that Android doesn't support UDEV, so having everything built in within the kernel is one good idea because everything is much easier this way. The only exception that you may find for that is usually around some drivers that may be loaded or unloaded, like the Wi-Fi chips, and those that require some specific firmware. So again, Bluetooth or Wi-Fi is pretty much the exception, or otherwise, if you have some properties drivers that you want to get out of the kernel tree, these are pretty much the only exceptions in terms of drivers. So you still can build modules, it's just not the common usage. So as for U-Boot, specifying in the board config.mk, you have the possibility to either have a pre-built kernel, or you can have the possibility to have the kernel being built as part of the AOSP. So depending on the variables that you may just specify, you just telling the AOSP build system whether or not to build your kernel for you. And what I would recommend to any kernel developers trying to build this new device is first, if you are trying to develop new drivers for your hardware, a good recommendation would be to make it happen and make them work under a regular GNU Linux system first, and then trying to port the differences and adapt them on Android. It's much, much easier to debug the hardware on Linux than it is with Android. One other thing that has changed within Android is the Bionic C library. Again, I won't spend a lot of time on that, but the major changes is that they have designed for many reasons, license, for example. They have designed some specific C library, which is non-POSIX, which has no support for locals, for C++ exceptions, and for many differences around threads, plus different runtime changes around user groups management. So for many reasons, they have designed their own C library. This is really different from the glibc, and we will see that it has some impact that has to be taken into account. So for example, still within this library, one thing that has been implemented or supported in Android is that the system has support for different kind of properties and settings. So this is, I would say, somehow like the registry database in Windows. You have the possibility to put or to declare some property and assign them a couple of values that the Android system knows. So Bionic has the capability to actually keep in memory this array of properties and values. So this is also one of the very specific things that they have done in the C library. And all these values can be simply get and set through either the get properties and set properties shell command, but they also can be done within the C API, but also within the Java API. Unfortunately, no documentation actually exists about the existing properties, so there are just a lot of properties that exist, but you have no exhaustive list that will tell you what are the properties and what are the default values. Every application just declares its own, and any application that you may write just can create new properties and assign any new values. So you're pretty much on your own on that. And the other possibility for Android to store the different kind of settings and configuration that you may have is to use some more persistent configuration settings. So the previous ones really were volatile, meaning that when you reboot the devices, any changes would have been lost. If you want to have persistent settings configuration, then they can be, and they are, put within an SQL database. So many applications just use their own SQLite database for the private data, but you also have some very specific, not specific, but very generic settings that exist. So for example, if you browse some Android devices, you have in the /data/data.com.android provider settings, you have the settings DB database, which you may find a couple of useful tables, for example, the secure and the system tables, and you also get a lot of properties within these tables. So this is pure SQLite, so if you want to hack around them, you can just use the SQLite 3 command in shell and just modify it or get all the properties that you have. And they are persistent, so they will survive at any reboot. So for example, here you may find for the network part, you may find the IP address, the DNS, the gateway, this kind of stuff. This can be stored within this kind of database. We will see later on that when we are trying to make our new devices, you probably always have to modify either the properties or the settings to customize a lot of things. Also, one thing that is really different within Android towards the regular GNU Linux system is the Android init. So the init that has been defined in Android has been completely written from scratch for Android, and it does way much more than just init, actually. It's based on the proprietary init language that they have defined, which is something that works through different rules and conditions. It is able to spawn different services and restart them in case of failures. And this is more than just init. It's also some binary daemon that actually goes on for the whole system life that the different application can interact with through signals and through Unix sockets. So what the init does is, in a few steps, actually, when it boots up, it creates the basic file system. So it creates the /dev, the /proc, the /sys, and mounts all this file system. Then it parses the init files, which are the /initrc file, which is the main file that is provided by Google, but you can modify this file if you want. And it also parses one file, which is /init, followed by the name of your hardware, .rc file. So if you want to modify or add new things within the init, you have the possibility either to modify this file or just to append new commands or new actions within this file. For many reasons, instead of using the board names, they are actually parsing the proc/CPU information. So depending on how you built your kernel, you may just watch out how you have named your board, because the board name really will be used by the init daemon. When it parses all these files, what it does is actually creating what we call exec queues. So it defines, again, depending on different rules and different conditions, it defines just a series of commands that needs to be executed. And then when trying to boot up, you get different triggers that happens. For example, the early init trigger, or the pre-file system, the file system condition, the post-file system condition, or the boot trigger. And every time the system goes on and goes to these different steps of the initialization, it just starts the actions and the commands that have been associated. So the next following slides are actually just a recapitulation of all the particularity of the init language from Android. So for defining, for example, the actions, what you have is the syntax is on trigger, then execute a list of commands. The trigger, as we've seen, can be the pre-file system, the file system, the boot state, different kind of stuff. But you can also define the services within this init program. So again, the services are persistent applications that will remain active, and it can be restarted or respawned on failure, and that are not necessarily started at the init of the device. So it's not because your service has been declared within init that the service will start automatically for you. So again, we will see probably with the Wi-Fi support, then, for example, it can be up to the user applications to actually talk to init, which will actually start the services for Wi-Fi. Also, you have some options and some comments that you may run. Here I just put some tables that you may look later on the slides, but this is the complete list of options that comes from for inits. Same goes for the triggers. So all of these slides will be available on the net. So if you want to just have a look at all the possible options that you may find for init, just have a look on these slides. There is pretty much no documentation from Android on this side, just one README file, but it's pretty much not up to date. And you also have the different init commands that are accepted by the init daemon. So it looks like shell mostly. So you may find some commands that you already know, like chmod, chown, hostname, ifup, and everything. But this is actually not shell. So again, it's their own specific language, and this is not the command from the shell, so neither from BusyBox, neither from Toolbox. This is pure re-implementation that are done in C. So you just can't do whatever you want within the init. It's really, really specific. So just take care when you are trying to modify the init. Again, so this was the list, the following list of all the commands. U-Event-D is also one useful daemon to look out. Actually, it shares the same code within init and U-Event-D, just depending on how the binary is called, that it defines which one is to be started. It somehow replaces udevd that you may find on the regular Linux, and it's mostly used to set the user, the group, and the permissions on the different nodes that you may find on /dev. So again, as for init, when it goes on, it just parses the /u-evend-d RC file. Yep. And it also parses the other files that match your hardware if such has been defined. So if you have some very specific driver for some specific hardware that you have, when it just brings up, for example, you may just want to, I don't know, change the user group, the user or the group. So this can be defined within this file, and this is up to you to declare the good rights for the file. Just again on this file, another one good thing that might be important for the triggers, which is somehow a capability for you to replace some capability of udev, are the device added and the device removed triggers. So for example, if you have some rule that just says device added /dev/my device, then you can put different actions. So if you want to do some really, really specific things on your system when, for example, your device driver has just popped up, then this is the way to do it. Also, one of the things that you may have to hack around when doing your own device is the HAL library for some hardware components. So as you probably know, the Android has been modified to do a lot of things, pretty much to allow you to do closed source things within the user space. So this is some kind of definition that I have made that makes some bridge between the kernel drivers that are really regular Linux implementations and the Android framework. So I won't go much further into the details of the different HAL components, because each HAL component is so complex that it's probably a 1-hour talk for each of them, so we won't have time for that. But most of the components that you may have to hack around is the audio components, the frame buffer, the GFX allocator, which is also known as Gralloc, the GFX hardware composer. So GFX allocator and the hardware composer usually are provided by your hardware manufacturer because they are really specific to your GPU, and you, as creating your new device, you usually don't have to modify these files. You may have, however, to modify the camera HAL component, which is really specific to the sensor that you may have chosen and to the different effects that you want to do with the camera. And the audio part, as I said, is also one really tricky component that you may have to hack. The audio HAL is actually responsible for binding the different audio sources and the different audio outputs that you may have, and make the bridge between this and the Android framework. So that, for example, it allows you to configure the different devices and tells you how to mix the different audio streams or to route the audio streams. So, for example, when Android receives a call, you may just want to shut down the volume on one device, for example, the loudspeakers, because they were playing some MP3, so you just want the volume to shut down and to have to put the volume up within the Bluetooth headset that you have, and just turn one off, turn one down, turn one up, this kind of stuff. So this is really, really specific to your device, and you may have to modify all of this. For the Wi-Fi HAL also, we have a few slides after that, but this is also where you make actually the bridge within within the Android framework and the low-level drivers, saying, oh, are we going to load this new driver, or are we going to remove it, or are we going to switch between client and access point mode for the Wi-Fi chip? So all of this might be specific. You may not need to modify a lot in this, but in some cases you still have to modify a few things, because you may find some chip or some that is not really working like the others, and you may have to work around that. Same goes for the GPS, the lights, and the different sensors, so you may have to modify that. So again, this hardware abstraction library consists of the different plugins that are loaded. So what is tricky is that these have to follow some API, which is barely documented for some devices at least. The API is defined in the hardware/liphardware include hardware directory within the AOSP, and Google provides some default implementation. In some cases, it doesn't do much, and so you have to re-implement your own. What is really important is that you have to implement the API that has been provided by Google, of course, because this is the only way for the Android framework to actually map and interact with the drivers below. And again, these are .so files that are dynamically loaded through DLOpen. So if you have badly written something, or if you just do not have taken care enough within the make files so that your library doesn't link with something, then you may just have the library not loading properly, or the functions not being called properly, and then you just have some runtime issue. But you won't, most of the time, you won't see that at build time. So this is also one really tricky point. And these modules are actually loaded at runtime, depending on on the name. So for example, first the system tries to look for the libraries within the vendor lib hardware directory, and then in the system lib hardware directory. So, and also depending on here you find the system properties, again, that has been defined. So you may have different implementations for your device for these HAL drivers. And depending on what are the ones that are available on your system, the Android system will just try to find the one that matches the best the device that you are trying to work on. Next is a couple of things that we have made. So this is really not completely Android specific, but at least for the implementation of our project. Again, we have taken the Linearo kernel, which is, if you have tested it, running on the Panda board, at least outputting everything on the HDMI components. So for example, in our phone, we do not have HDMI output. We just want to output within the LCD, which may sound not that difficult, but if you want to have a look, this is really easy to just replace the HDMI driver by the LCD one. So for example, in our case, the only thing that we have to do, if you check out the kernel board configuration of the Panda board, you just have to specify that you do not want HDMI anymore, but you want to use an LCD device. You want it to be the preferred default device, so that you're really sure that it never gets to init the HDMI. And you may just want to specify, for example, create a new panel description that matches your screen. So that's what I do with my DPI LCD panel. And when you just need to hack the driver's video map to panel generic DPI system and create one new configuration for your device. So in our case, we just have a wide VGA 800 through 480 pixels. You just set up the different clock rates, timings, and so on. And you just, again, have to match the name which is my DPI LCD panel, and then again, this is not Android specific, but really Linux centric, and you just manage to actually make everything from Android output from the HDMI to LCD. One of the things that we also have seen when we went into booting the board was the tablet mode support. Actually, as I said, we were using an LCD screen, which is a wide VGA 7 inches. So if you calculate the aspect ratio, it makes a 133 DPI, which is actually a bad thing for Android, because depending on the DPI, Android actually decides whether it boots in phone modes or in tablet modes, at least for the UI. So in our case, this is not a tablet, it has no orientation, but Android was just saying, okay, the screen is too small, so I considered that this is booting in phone mode. So we do not want that. So what we do for that is just modify the board config.mk, and then you just reuse this macro specifying that's the product property. You just want to override the arrow.sf LCD density and just say, okay, this is not 133, this is 120. And this 120 has been hard-coded in Google code to say, okay, below this resolution, then I just consider it's a tablet and it just boots up with the proper orientation. Again, what you might want to do, still regarding the orientation, is modifying, or specifically not modifying, but creating or modifying the overlay files that I've presented earlier. And so modifying the config.xml file, just saying that, okay, I want these three specific properties to be set in order not to allow the screen and the different applications to switch the screen between portrait and landscape mode. So this may just, again, trick Android, and he has no clue whatsoever. Then you want to have, you probably, at this point, you have a device that runs on your LCD, so just as boot up, and you have Android running on your device. It's pretty much a good step. Now you want to have support for the GPU, which is pretty mandatory, at least for ICS, because everything now is using 3D and OpenGL. Without that, it's really super slow. So what you need to do is, again, modify the board config.mk file and specify a few new rules as to provide the support for the Graloc HAL module, but also for the OpenGL GLES 1.x and 2.x modules that have been provided by your vendor. So you just want to deploy them into the /vendor, and for that, you just modify the board config.mk file and modify a lot of things in order just to say, put these files and include them in my system image. And again, even with that, normally Android is supposed to actually be able to auto-detect that you have 3D and to auto-detect which version of OpenGL it is running. In some cases, some applications just crash because they are not able to support or to detect OpenGL versions. So one common hack that you may just have to do is, once again, modify the board config.mk and override one property, which is the arrow.opengl ES version, and you just put this magic number, which is some binary number saying that it is compatible with OpenGL ES 2.x, and then you got 3D supports in many applications, for example, Angry Birds, and if Angry Birds works, everybody's happy. So again, one tricky thing that we had was the input subsystem. This is also one thing that has pretty much changed between Android 2.x and 3.x, and also between the 4.x. So this is actually one good thing. It's one of the subsystems that has been pretty much documented by Google, contrary to the others. Again, there has been some changes in 4.0, but at least it has been a bit documented. So the usual stuff that you have within Linux, at least, are these parts, meaning that you have the support for the hardware, like, for example, a USB device like a keyboard or a touchscreen that can be wired through I2C. And then within the kernel space, you just implement drivers that have to, which the role is to actually map the hardware and just create some Linux EVDev events that are the reference way to provide the input information to the applications. And what Android does on that is that they have created some daemon which is called the Event Hub, which actually fetches all the EVDev raw scan codes from Android drivers, and then they just forward these scan codes to another service from Android, which is the input reader. And the input reader is one important thing because he keeps the different raw scan codes from Linux drivers, and it also has to map them with three different kind of files from the user space, which are the device configuration files, .idc, the keyboard layout, and the mapping table. So we will see just after that, but it's only the goal of the input reader is actually to make some mapping between the raw scan codes that you see below and these definitions that you may see or define in the user space. And then it provides some new scan codes which are not Linux compatible, but which are really Android key codes. And then it forwards them to the input dispatcher, which has the responsibility to provide them back to the application. So we'll see that with an example for the touchscreen afterwards. But here you may just find more information about the input key layout files. So again, one of the goals is to map the Linux keys key code into Android key codes. This is required not for touchscreen, but at least for all devices that have physical keys. So for example, the keyboards. This is really important. And what the system does, or what not the system, but at least the input reader does, is actually looking for files first within the system uShare key layout, and otherwise within the data system device key layout directories. And it tries to find some matches between your hardware and the mapping that can be done. So first, it just tries to look, for example, for the vendor and the product, or potentially the version also, or for the device name, or at the very least for the generic. So it can use the USB ID or the USB vendor ID to determine what is the match between your hardware or not. In most of the cases, mostly for a keyboard, the generic implementation should be okay. But if you want to remap all the keys the way you want, just create some .kl file that maps everything the way you want. This is also some documentation that you may have to use if you want to create your own KL file. This is the way you can do that. So the only thing that you have to do is to put the Linux scan code, and then you just put next to that the mapping for the Android key code that you want to be displayed. Also, you may have some policy flags that you may want to add. So, for example, the wake one, which is described over there, is really important. This just allows Android to wake the system up in case it was in suspend when the key has been pressed. Same goes for the configuration file. So this is, by opposition to the keyboards, these IDC files also are looked within the same kind of directories. So system first, data then, and they are trying to match the right one depending on the device that you have. But they are actually optional for HAD keyboard or mouses, but they are absolutely mandatory for touchscreen, for example. So these are the files that actually says this is one touchscreen. It is aware of the orientation. It has some proximity detection support. So this is something that really tries to explain to the event reader from Android what is the devices that you are actually getting scan codes from. And without this file, Android just do not forward anymore any events to the upper layer. So one of the big issue that many people trying to migrate from Gingerbread to ICS found out, at least for the touchscreens, that this kind of file was not mandatory between ICS. It is now. And so most of the guys just have the drivers, and it was not working anymore, or at least they thought it wasn't working anymore, but the only difference was that the events were not propagated. So again, I just put some, if you want to hack around and create your own device or driver for the touchscreen, this is just some explanation. So again, the driver has to, for the touchscreen at least, the driver has to provide the correct position to the screen. So contrary to what you may find with Xorg, there is no upper driver that would try to match the virtual resolution of the screen and the virtual resolution of the touch screen. Then you have to modify, of course, your board configuration within the kernel in order to, well, that's just one thing, but correctly configure the different GPIOs and multiplexing of the different pins of your board. And then you just want to register a new device. So for example, this is for the pen board, a couple of structures that have to be defined. So this one is the function that just register the new device on the bus. And one thing that you have to really take care is the driver name. So we'll see why, but this one is really important. And when you go directly within the touchscreen drivers, so this is still in the kernel, but not in the board configuration, really the touchscreen drivers. This is, I've put in red the things that are now mandatory in ICS that were not mandatory in Gingerbread. So this is really important. Again, the driver name. So this driver name has to be the exact same name that the IDC file has to be named on. So otherwise, this is the only way for the input reader to actually match the driver and the IDC file. And again, in red, I've just put some new things that many drivers already implemented that, some didn't. And for example, for ICS, now you just absolutely need to force the pressure. So even you may have multiple thresholds for pressure, but even 0 and 1 saying on and off is enough for Android. But you have to declare that, and you also have to send the event button touch, which is really important. This was not mandatory, it is now. So if you have to modify your drivers for the touchscreen, just take care of these functions and be sure they are implemented. So again, as I said, you now need to have some IDC files. So just check out that, ensure that the name that you use for your IDC file is the exact same name that you have defined your driver. And again, you just have to modify the device.mk file and just modify the product copy files, saying that this IDC file that I have in my build environment, I want it to be within my system image. And just below, I just give you some example of the IDC files that I use for my touchscreen. So as you can see, it doesn't do much. The only thing it does is telling Android input reader that this is a touchscreen. This is not a mouse or other kind of pointers. It's really touch. And I'm not orientation aware. So this is important for us, and maybe also for if you define some tablets, if you are just switching your tablets from portrait to landscape, then specifying one in this line just permutes the X and the Y coordinates within the drivers. Not within the drivers, but at least within the input reader. So just specifying that changes everything. One more thing about the storage subsystems. So this may also change depending on the topology of your SD card. Also, you may have multiple SD cards or multiple USB devices. But you may want to modify or overlay the frameworks-based storage list XML file, just saying that I have some mount point that I want to be MNT SD card. I want it to be declared as the primary storage system, and this is not something removable because, for example, this is my internal SD card slot. If you have a second SD card slot that you expect to use for user data, for example, then just create some new mount points and just say this is not the primary, but this one is removable. And this will be used and also this one will be used by the volume daemon in order to actually map the physical device and mount it at the right directory. Again, on the audio subsystems, you also have to define, once again, in board config.mk, you have to specify that your board uses audio and you want it to be enabled so that all the applications get compiled in. And you must, and this is absolutely a must, you must implement the audio HAL. So for the pen board, this was not implemented at all. Google has released the ICS, which was supporting the pen board officially. It has been released in last October. There was no audio. The audio support has been added in January and only for output, and the input only has been added like 2 weeks ago, sorry. So this continue to evolve, and it's still not completely done. And if you are doing your own device, you also still have to modify this file. And again, I won't go further on that, but this is the audio HAL that is really responsible for getting and setting the volumes, the mute, the gain, configuring and routing the different interfaces that you may have on your sound card, this kind of thing. One new thing that has been done in ICS towards the others is that they are no longer using the regular ALSA library. They are using Tiny ALSA, which is pretty much the same, except it's a bit more lightweight, and it's not the same license, which is more Google-friendly, meaning it's not GPL anymore. Your new audio library, just, again, it's one SO file that is using a DL open, so if you link with the bad library, which is no longer there, the file will still compile, but at the runtime you will get no audio at all. So just take care to link it against the new Tiny ALSA library and to make sure to modify the right thing. I've put some example from Linearo, for example, of the implementation of the audio HAL for ALMAP 4 if you want. So just have a look at this. One more thing that we have to deal with was the network and the connectivity. This one was real pain because network and connectivity within Android is really, really different than what you may expect with Linux. So with Linux, again, it pretty much stops here. So you have the hardware, you have some Ethernet driver or some Wi-Fi driver, and it works, and everybody's happy. We'll see that with Android, actually, all the Java applications that want to access to network usually have to deal with a lot of new services, and it's pretty much all the Java framework that has been exposed over the different presentation this morning. But you get some connectivity manager and connectivity service. One has to be specific for the Ethernet, one has to be specific for Wi-Fi. Actually, one has to be specific for any kind of connectivity interface that you may have. They are responsible for example, configuring your device. So for example, the connectivity service, or at least the Ethernet or Wi-Fi service, has some ways to actually get access to secure settings SQLite database. So this is where you can store the IP address, the DNS, the gateway, this kind of stuff. And they just read them back at boot and try to reconfigure your interface. This is one good thing, but this is not enough, because in the end, you actually, every time your Java application tries to connect to the internet, well, to actually anything, it just has to go through the different Java classes. And it's not just a direct connection to the IP stack. So there are a lot of things that has to be done, for example, on the Wi-Fi state machine and the Ethernet state machine. Also for support of the proxy, many things have to be done. And we'll see with the Ethernet, for example, a bit later on. But again, for this Ethernet and connectivity, you may also have to overlay some resources. So once again, you have to edit the config.xml file. And within this file, you may just change some line specifying the network attributes and the radio attributes, which defines what are the interfaces that your board is actually supporting. So for example, on my board, I have the Wi-Fi, the Bluetooth, and the Ethernet. I have no GSM, no CDMA, nothing else. So I just want Android to know that these are the interfaces that are available to me. So what we wanted to add it against in our device was a device that is actually, we have Wi-Fi, but only as an access point. So we do not use Wi-Fi as a client or station mode. And we do not have any other 3G GSM access. So what we want to do is access through Ethernet, which actually it seems normal to any people that has made any Linux development. It's just an Ethernet device and internet interface, so it's not that much of a big deal. For Android, it is. So the guys at Google have just defined that Ethernet is something that will be supported one day, but they never made anything for it to be supported. So there is no connection no Ethernet connection supports within ICS up to now. So there is some patches that has been made by the x86 Android fork to support Ethernet that also has been integrated within Linearo, which is called the ECM, or Ethernet Connection Manager. So this is actually the kind of thing that we were talking about here, the Ethernet service and the Ethernet manager. They've implemented some state machine, and they have support for the secure settings database, which means that actually when you are just using Ethernet, you now have some possibility within the settings applications to define whether you want to have a DHCP addressing or static addressing, specifying your IP address and so on. And that's pretty much all about it. So your connection you just have your Ethernet interface that has been brought up to life and nothing else. So the problem that we have seen is that everything was configured. You just use ADB shell. You can do some ping, or some route. The network was okay. You can use wget. Everything was doing fine. And still no Java application was able to actually go out on the network. So this is called as the no internet connection symptom, meaning that from Android standpoint, at least for applications, it still has no idea that the device is actually getting the network connected to anything. So no application was capable of going out except from the browser. And the reason for that is that the browser uses WebKit, and WebKit uses regular C implementation of the sockets, which works just fine, like any regular Linux implementation. But all other Java applications that just have no idea that Ethernet is actually existing. And so what is actually missing right now is that the Ethernet connection has no real connection to the connectivity manager, so the Android applications still have no idea that some connection is here. So this has to be implemented. It's still not the case in Android. And also one important thing at least for enterprise and the business I'm working on, is the support for HTTP, for the HTTP proxy, sorry. This is also something that is not supported by Android because most of the tablets and everything, they just have a 3G connection. There is no proxy. They don't care about that. When you're putting it in an enterprise, most of you probably all are behind proxy. Android has no idea how to go over there. It has some ideas going how to go over there in Wi-Fi, but not in Ethernet. So once again, this is some place where Android is completely stuck. Speaking about Wi-Fi, you obviously have to support the kernel drivers and the associated firmwares if you want the Wi-Fi chip to work. And you have to actually modify the HAL component in order for the Wi-Fi to work. So the HAL component is located, the HAL driver is located in hardware/lib/hardware/legacy/Wi-Fi directory. And the default implementation should be pretty much okay for all the devices that you have. And what it does actually is trying to load up or unload the Wi-Fi driver and just try to actually configure or init the WPA supplicant service. So the WPA supplicant service is something that has been defined within the init RC file. So once again, you see some link between the HAL and the init, and actually when you are just hitting the Wi-Fi on/off within your settings applications, it goes down all the way down within your Java stack up to the Wi-Fi HAL, which actually use some Unix sockets to ask the init daemon to actually start the WPA supplicant application. And so if you want to change something within the Wi-Fi or something like that, actually you may not only have to modify the HAL, you may also have to modify the init RC file. So this is a lot of things that have to be modified. Same goes for the access point support. And still speaking about the connectivity, the Bluetooth is a bit better supported, but you still have to modify a couple things that, once again, in the board config.mk file, you have to, once again, specify some variables saying that board have Bluetooth so that all the Bluetooth components gets compiled in. And Google also have made some very specific libbluedroid interface, which is just, once again, one more layer that has been defined by Google, used to interface within the chipsets and the different Bluetooth service. I don't know why they haven't made it like a regular HAL driver like the others, but so it is. And for the Bluetooth, but also same goes for the Wi-Fi. what you have to do, once again, is to modify the system etc permission file and add some new XML files specifying that your hardware supports Bluetooth. And same has to be done for the Wi-Fi. Otherwise, if you do not have this file, you just never get to see one on-off button within the settings applications, for example. So this may sound really stupid, but the only presence or non-presence of these files determines the complete behavior of your system. Regarding the multimedia subsystem, most of the work is usually done by your SoC vendor. So it is really pretty uncommon that you have to modify that. The only thing that you may want to modify is the media.profiles.xml file, which is important if you want to specify what are the encoders capability of your system. So this is one XML file, once again, that defines, okay, my board is capable of encoding in H.264, but at this minimum bitrate, this maximum bitrate, same goes for the resolution. So if you want to restrict the resolution of your encoder for any reason, this can be done in this file. So far, although it's only supporting the encoder capabilities and not the decoder capabilities. And for the rest, but once again, it's pretty much done by the vendor in most of the cases. You once again have to modify the board config MK file, and you have to compile and provide support for all the OpenBricks wrappers that are needed by stage fright from Android in order to actually access to the hardware encoding decoding engine. One more thing that we have done also is, as I said, is our device is always connected, which is not the case of most of the Android devices. So we have made some change that is quite popular around the internet, which is some trick that just prevents Android from saying that we do not have battery, and so just popping up some icons. So what we have done is create one, still using the device.mk, we have just added product property overrides, and we have created our own hardware.noBattery property. So again, the only rule is that you can put whatever property name that you want and associated value. There is no naming convention about that, but we just create our own, and we have modified the battery service in order just to check if this property exists. So once again, this can be done directly within Java API using system properties get function. And if this property has been set, what we do is actually not starting the battery observer. And with that, we just create some stub that just tells Android, okay, the battery is always connected and it's always full and everything. And so it won't bother anymore about the battery. Speaking about the phone, because our device actually is a phone, or we want it to be a phone, but as we've seen from Google's standpoint, a phone is something with a modem, with a GSM modem, and we are not. So the least that we can do right now is, once again, to overlay some resources in the frameworks-based config.xml file, and at least enabling or disabling a couple of interesting ones. So for example, we just say, just modify the config voice capable, saying, okay, this device do not have telephony support the way that Google believes it is. We are not capable of sending SMS either. So this determines a lot of stuff, and the runtime saying what are the applications that run or not. And by opposition, what we want to do, because this is an IP phone, is that we want SIP support. So this once again, the setting name is config SIP Wi-Fi only. So once again, we say that for Google and Android standpoints, voice over IP is Wi-Fi, because anything else from Wi-Fi doesn't exist for Google's standpoint. And we also want to enable some more setting about the SIP. So what's more about that? Because we're already late for 10 minutes. Of course, more devices has to be supported and described. So for example, how to completely get rid of modem and the reel of the camera and the GPS sensors. So this really is a lot of work to be done, but once again, this needs much more time for me to explain you all of that, and it's really another story for another day. So thank you very much. And you.